everyone! Today I want to talk about a convolutional neural network that I built using Rust. Last year I went through Daniel Bourke's PyTorch course on Free Code Camp, which was really good by the way, and as part of that tutorial he makes a CNN using FashionMNIST data. So the M in MNIST stands for modified, and that's there because the data was pre-processed to be used with machine learning. The NIST part stands for National Institute of Standard and Technology, which is the agency that originally collected this data. So this dataset, FashionMNIST, is basically a large dataset of images of clothing. The model is supposed to successfully identify items of clothing when shown them after training. With the help of that tutorial, I got this working fine in Python using Google Colab, but I recently looked back at the repo where I did this project and I wondered if I could do it in Rust. So what is a CNN, first of all? A convolutional neural network is a type of neural network designed specifically for images. Instead of looking at the whole image at once, it scans across it with small filters, say a 3x3 patch of pixels at a time, and learns what patterns to look for in those patches. Early layers pick up on simple stuff like edges and corners. Later layers combine those into more complex shapes like curves or textures. The convolutional part just describes that scanning operation mathematically. Stack a few of these layers together, shrink the image down at each step so the network is looking at bigger and bigger picture regions, and eventually you have something that can classify what's actually in the image pretty reliably. So enter Bourke. Bourke is a deep learning framework that's written entirely in Rust. A lot of ML tooling in other languages is really just a thin wrapper around libtorch in disguise, and libtorch is a big C++ library that powers PyTorch under the hood. Bourke doesn't really do that. It's pure Rust, so it means no giant C++ dependency to install. And the whole thing compiles with cargo, like any other Rust project, and you still get the stuff you'd expect from a real framework. You have automatic differentiation, an optimizer library, dataset and data loader utilities, and a training loop with metrics and checkpointing. So Bourke is also backend agnostic. The same model code can run on a CPU backend or on a GPU through WGPU or CUDA just by swapping out a type. And I actually ended up taking advantage of this, which I'll get to in a bit. But first, here's how I actually built the CNN. So the first thing I needed was the data. In the Python version, TorchVision just hands you FashionMNIST with one function call. Bourke has MNIST built in, but not FashionMNIST, so I wrote that part myself. It turns out FashionMNIST ships in the same exact format as the original MNIST, which are these IDX binary files. So I wrote a little downloader that grabs the 4 gzip files from Zalando's mirror, unzips them, and parses the raw bytes into images and labels. It caches them locally so it only downloads once. And then there's the batcher that turns a stack of images into a tensor and scales the pixel values from 0 to 255 down to 0 to 1, which is exactly what PyTorch's 2-tensor transform does. Next was the model itself. This is a port of the TinyVGG architecture. A VGG stands for Visual Geometry Group, which was a well-known CNN that came out of Oxford in 2014. The idea was basically just to stack convolutions as deep as possible and see how far that gets you. TinyVGG keeps the same structure but scaled way down, small enough to train quickly and easy to understand. The architecture is 2 convolutional blocks followed by a classifier. A block is just a named group of layers that do one conceptual job together, and here the block runs 2 convolutions, applies a ReLU after each one, and then finishes with a max pooling layer. ReLU stands for Rectified Linear Unit, which is a fancy name for a pretty simple thing. If the value coming out of a convolution is negative, zero it out. If it's positive, pass it through unchanged. The reason you need this is that without some kind of non-linearity between the layers, stacking convolutions doesn't actually help you mathematically. It's just a chain of linear operations that would collapse down into a single linear operation, no matter how deep you go. ReLU breaks that, which is what lets deep networks learn complex patterns. Max pooling is the shrinking step. It takes a 2x2 patch of the feature map, keeps only the largest value, and moves on to the next patch. That cuts the width and height in half. So the input images start at 28 by 28. The first block takes that down to 14 by 14, and the second block takes that down to 7 by 7. After the two blocks comes the classifier. That's the part that actually makes a prediction. At this point, the network has squashed the image down to a 7 by 7 grid with 10 feature channels. So I flatten that out into a vector of 490 numbers and feed it through a single linear layer that outputs 10 values, one per clothing category, whichever output is highest in the prediction. The whole network is just under 7,800 parameters, which is actually tiny as far as neural networks go. In REST, this ends up being a pretty clean implementation. You define a struct that holds your layers, you derive Bourke's module trait on it, and you write a forward function that describes how data flows through. Then, to plug in Bourke's training loop, you implement two traits. One that says, here's how to do the training step, i.e. running the forward pass, computing the loss, and backpropagation, and then you have one that says, here's how to do a validation step. The loss function is cross-entropy, same as the Python version. For training, I use Bourke's high-level learner. You hand it your model, an optimizer, and your data loaders, and you tell it which metrics you care about, and then it runs the whole thing for you, including a live dashboard showing accuracy and loss as it trains, which I thought was really cool. I kept all the hyperparameters identical to the original course by Bourke, stochastic gradient descent with a learning rate of 0.1, a batch size of 32, and trained for 3 epochs. So I originally had training set up to run on the CPU backend, and when I first tried it on this machine, the progress bar came up and said it was going to take 12 hours! And I don't know about you, but I have other things to do, and 12 hours was a really long time for a really tiny model like this. Which, okay, convolutions are generally a lot of math. Every conv layer is sliding a little filter across the whole image and doing multiply adds at every position across 60,000 images, 3 times over. So the CPU was sitting at 91% util, but honestly, 12 hours is still a little bit much. And this is where the backend agnostic thing that I mentioned earlier actually comes in handy. Bourke has a WGPU backend that can run on any GPU. It uses whatever graphics API is available on the system, so DirectX, Vulkan, Metal, whatever you have. And switching to it was literally just changing the backend type in the main RS file and adding one line to cargo toml. The model definition, the training loop, and the data loading, none of that changed at all. The backend type that gets passed around as a generic is the only thing that's different. I pointed it at WGPU device default device, which automatically picks up the best GPU it can find on the machine, and the training time dropped dramatically. So after training finishes, Bourke prints a summary table showing accuracy and loss across all 3 epochs, split by training data and validation data. The validation split is the one that matters. That's the 10,000 test images the model never saw during training. It came in at about 88%, which lines up almost exactly with what I got in Python. The thing I was watching for was whether the training accuracy or validation accuracy stayed close to each other. If training accuracy shoots way up but validation stays low, that's overfitting. The model just memorized the training data and can't really generalize. Here, they ended up within 0.5% of each other, which is a pretty good sign. The model is actually learning something, not just pattern matching the examples that it was shown. And just to make it concrete, at the end of training, it runs predictions on 9 test images and prints out what it guessed versus the real answer. So things like an ankle boot, pants, shirts, sandals, all correctly identified on this run. So the other thing I wanted was to not have to retrain the model every time I wanted to use it. So once the model is trained, it gets saved to disk. And when you run the program, you actually get a little menu. So option 1 trains a fresh model. Option 2 loads the saved one and runs a prediction. If you pick option 2 before you've ever trained, it catches that right away and drops you back into the menu instead of crashing, because originally it just crashed. One other thing worth mentioning is what happens if you stop training partway through. So Bourke's training dashboard has a quit button, but when you hit it, Bourke internally panics to kill its training threads, which normally just dumps a bunch of ugly output to the terminal. I wrap the training call in catch unwind so that the panic gets caught, the artificial artifacts on disk get cleaned up, and then you're dropped back into the menu cleanly. If you decide to stop and start over, it just works a little bit easier now. So once you do have a model, you give it the number of any test image from the dataset. And it draws that image right in the terminal as ASCII art, which I thought was a little fun. So you can actually see the piece of clothing directly there. Because, as developers, we all live in our terminals, and I wanted it to be in the terminal. Underneath this, it tells you what the model thinks the picture is and what it actually is. So you can just sit there and flip through the images and watch it call them out. But the model is not perfect, of course. The categories it struggles with are the ones that you'd expect, the ambiguous ones. So sometimes, even in real life, I can't tell what someone is wearing because fashion is weird. Like, man, is that a shirt or a jacket? And with these pictures, some items do look ambiguous as a low-res grayscale blob, so I can give the model some slack here. If you go hunting, you can find images where it guesses wrong, and it generally is ambiguous, and that 88% number suddenly makes a lot of sense. So yeah, that's the project. A convolutional neural network ported over from PyTorch, rebuilt in Rust with Burn. As always, if you want to try it yourself, the repo link is in the description below. And thanks for watching. Bye!